at the end. Yeah, I'll just get started. So I want to tell you about Poly. I've given several versions of this talk before, but there are some new things in this one. Hopefully it's enough. So hopefully you'll enjoy it. So personally, I always thought I could understand myself and everything that mattered to me in terms of math. It was a pretty naive belief, but it's one that I've gotten a lot of mileage out of. So it was kind of a faith, religious faith almost, that has actually been okay for me. And but what I thought was, if we're talking in natural language, I don't know how old I was, maybe 5 when I kind of had a vague idea of this, but like as I progressed, I think what I was thinking is like, what can't we say in math? Why can't we say, if we can say circle in math, why can't we say I need food in math? So what is anything we say to each other inherently precluded from mathematical expression, and what things are and what things aren't? And when I finally learned category theory, I thought, aha, this is where I can say everything. It's a sublanguage of math that can talk about math, and it's clean and principled and structural and expressive. And I really loved it. And so I got to work trying to understand all the things I care about in that world. And to some extent, well, I guess I'll get there. So what can we say about self-life and world? Well, I first assumed, okay, everything is just information all the way down, and our minds are information storage devices. Let's just say that and see how far we can get. And so we communicate with each other and with reality somehow, maybe by what? Sending each other data or something? Is that what's going on? And so I thought about categories as like the shape of the data, and then set valued functors as the actual data and examples we have. And then what are called parametric right adjoints turned out to be what I thought were the nice data migration functors that send data from one database or person or something to another. But when I was doing work with companies to try to tell them about this stuff, they would tell me about interacting processes, and that seemed really nice and categorical, but it didn't fit at all into my story. So then I said, oh, aha, I know what everything is now. Everything in the world is interacting dynamical systems. My brain is got a bunch of neurons, and they're organized in populations, and me and my liver and all sorts of things are sending each other information, or transistors and are organized into logic gates, which are organized into adder circuits. And that's what's really going on, is that there's just machines constantly sending each other information, and that's what we really should see. But then when we were working with NASA on thinking about airplanes, the airplanes would pass each other, and sometimes they would be wired and sometimes they wouldn't be wired together. And so sometimes I'm sending you information, like right now, maybe I'm looking at your faces to see if you're following or not, and then you're listening to me and stuff, but we're not wired together forever. Like we decided, you and I, to press our join Zoom button, and that's why we're wired together. So that didn't seem to work. And so then one day I met Poly and I fell in love, and as Jonathan Laurent says, I guess I'm polyamorous. But it captures dynamical systems and what David Jasmyers calls rewiring diagrams. So as a way of this picture here on the bottom could, the various x1, x2, x3, you, me, and my computer can rewire to each other based on our internal states. But what I really loved about Poly was not just that it could do that, but that it's so well behaved mathematically. It's a place that you can really get to work in and expect good formal, and there's a lot of good formal properties. So when I looked at the dynamics, it looked like it was all about comonoids. And so I asked my friend and colleague Joachim about what are comonoids in Poly, and he pointed me to Richard Garner, and I found Richard Garner's hottest polynomial video, which I really love that name. It's I guess Chris Kapulkin and Dan Christensen's seminar, and in Richard Garner's hottest polynomial talk, he explained a result of Am and Ustalu, which is comonoids or categories. In some sense, this whole talk and the previous ones have just been trying to advertise how cool I think Garner's result following Am and Ustalu's result. Garner's result is that bimodules in Poly are parametric right adjoints, which you might remember are the data migration functors from before. How cool all those results are. So that's kind of what I want to talk about. But anyway, the point is that I came to it from dynamics, and then what I found when I got there was the database story again. So I was overwhelmed by Poly's elegance and capacity for applications, that it's so computational, hands-on. It's all about set and set up, and it has such great formal properties. Like, yeah. So I wanted to, I use Poly when I'm thinking, like, I like to think about philosophy. And so I use it to think about that stuff. I want to know, like, what does it mean that I can manipulate objects? I can somehow decide to wire to an object or to send it information and then move it all around and then let go of it and stuff. What is biological reproduction? Like, not like the deep evolved story that we have that's so incredible, but just like from this kind of automata point of view, where a mother, say, is able to gather resources from her environment and put them together in a way that creates another amazing human being. What would you do to do that at a minimal scale? Or, I don't know, questions about if it's always now, like it's now, right now, right? We're here, we're always now, but then how do we perceive events that unfold over time? What's going on with time, you know? And what is survival? If the ship of Theseus question, if we change over time, what is it that survives? Just, can we ask those same questions, but of little machines that wire together based on their own internal states? And so if you're interested in, I take long walks with David Jas Myers, for example, or other people. We just sit around and think about philosophy, but we do it grounded in math. So if we're ever together in real life again, I'd love to talk to you about all these sorts of things. So the plan for the talk today is I'll first go into theory. I'll define Poly and one of its monoidal structures, whose comonoids are categories, coalgebras are copresheaves, and monoids generalize operads and operad algebras. And then I'll go into applications and talk about dynamical systems, databases, and cellular automata. And then I'll conclude by telling you some upcoming events and summarize. But you can think of this whole talk as kind of like a calling card that says, if you think any of this is interesting, reach out and I'm happy to discuss. Because I think there's lots of open questions here, both philosophical and in terms of the math and in terms of applications, like how we would actually implement these things in a computer. And so, yeah, please reach out if you're interested. Okay, so I'll start with something that in a lot of the talks, I say the same thing. So, but you might just, here it is again. Okay, so the category Poly has many names. It's the free, completely distributed category on one object. That means it has sums and products can depend on the sums and distribute over them. Some people call it the internal axiom of choice, or the type theoretic axiom of choice. It's the free coproduct completion of set op. So take set op and freely add coproducts and you've got Poly. Or take all the functors from set to set and look at those that preserve connected limits. And that's Poly. Or you take the full subcategory of functors from set to set, look at the representables and freely add coproducts. That's a lot like the second one. Or you might think of it most kind of operationally, I guess, as pairs of like typed sets. So the objects are a pair of a set S and a functor from that for every object in that set or every element in that set, I give you a set. And a map between them from S to S prime is a function from S to S prime, which I'll call phi1. And then this phi sharp thing that goes from S1 tau prime to tau. So for every element in S, it gives you a function from the set over here to the set over here. And when this phi sharp is an iso, then we would call this map Cartesian. That'll come later, but later you'll hear me say phi sharp is an iso, and then I'll say, and that means it's Cartesian, and that'll be, maybe you'll remember what I'm talking about. But it's not, you don't need to remember any of this stuff, or you can remember whichever one you like the best. Although the one we'll be working with the most is this one here. Poly is the full subcategory of all functors from set to set spanned by coproducts of representables. So another way to say it, though, is much more simply, I like to write it like this: y squared plus 3y plus 2 is a polynomial. It is y plus 1 times y plus 2 if you care. All the plus and times work correctly. They are coproduct and product. Or you can look at it as a bundle picture or a corolla forest. So in the algebraic picture, apply it to the one element set. And what you'll get is 1 squared plus 3 times 1 plus 2, and that's 6. And those are the 6 things down here, the 6 dots. And above every dot is the exponent there. So this exponent is here, 2, 1, 1, 1, 0, 0. And so that's the bundle picture of this polynomial. This is the one that in Gambino and Cox's paper, which is probably my favorite or most important, I don't know how to say it, paper on this subject. That's how they would think of it. But I also like this Corolla Forest point of view, which is that there are 6 dots here and each one has some number of arrows coming out of it. And we'll see why that's a nice viewpoint later for composition. I call the dots positions. So this thing has 6 positions and each position has some number of directions. And that will really bother people like, perhaps like the container folks who would call these dots shapes and would call the arrows positions. So there's a conflict there. I'm calling them positions because when I think of these as direction fields or vector fields, dynamical systems, these will be like the positions. And also because when we think of comonoids and poly as categories, these positions will be called objects. So the positions of the category are the objects, and the directions from any object are the outgoing arrows. So directions are like arrows, and that terminology fits both with the vector field dynamical system point of view and the categories point of view. So one way to think about this, different interpretations of this thing, is that every corolla, each of these 6 things is a decision, and its leaves are the options. So in this decision, you have 2 options. In this decision, you only have 1 option. You just got to go through it. Sorry, buddy. And in this one, you have no options, so you're done. You stay there forever. Okay, whoops, wrong way. Okay, so here's y cubed plus 2y, and here's y to the 4th plus y squared plus 2, y to the 0 plus y to the 0. And a morphism from P to Q delegates each P decision to a Q decision and then passes back the options. So maybe decision 1 is delegated to Q's decision 1, and decision 2 is delegated to Q's decision 1, and decision 3 is delegated to Q's decision 4. And then if you delegate 1 to 1, then all of 1's options are passed back or interpreted as options for P. So how would we think of a map from y squared plus y to the 6th to y to the 52? Well, imagine you have to pick heads or tails, or you might have to pick a number 1 through 6, like from a die. And you delegate that to a card deck. And you say, if I ever have to roll a die, pick heads or tails, I will use the ace of spades as a heads and all my other cards as tails. And I will take the rank of the card, and if it's less than 6, I'll use that rank. And if it's 6 or more, I will use 6. But any way you could do that to delegate the decision from your dice or card, your dice or coin decision to a card making decision would be a map of polynomial functors. So we really stop thinking of them as functors so much and start thinking of them as combinatorial objects. So the way, as I said, my favorite description, I think, is that poly is the category of sums of representable functors. And what's a representable functor? It's a functor like this. I write y to the s, y for Ioneta, and also because it looks like a variable, this is the functor represented by s. And a polynomial is just a sum of representable functors. So when I write p parenthesis 5, I mean apply p to 5, plug 5 in for y. But when I write p bracket I mean the set of directions in the ith position. So a morphism of polynomials is just a natural transformation. And as I said before, plus is coproduct and times is product. I don't know how much I need this, but just in case I do, if you plug in 1 for y, you just get I out, as I said before. So I sometimes rewrite this polynomial without anything but p's in it. So it's p of 1 is a set of positions in the polynomial. And for every position, p bracket I is the set of directions there. Now, probably the really nice monoidal structure is composite. You can take 2 polynomials and get a polynomial. And I write that composite by p triangle q, and there's a reason for that. There's several. One is that it looks like a circle. So this is like p circ q. And the only reason I don't use circle is that I usually want to reserve circle for composing morphisms. And I think of polynomial functors as objects. I think of the natural transformations as the morphisms. But there's other reasons we'll see in a second for why I like this triangle shape. So y squared, if I take p compose q for y squared and y plus 1, it means take q squared, which is y squared plus 2y plus 1. So that's an example. But it's not a symmetric monoidal structure. I just wanted to note it's only monoidal, not symmetric monoidal, because q composed p is not p composed q. It's y squared plus 1 instead of y squared plus 2y plus 1. Finally, the identity functor is the unit. So p composed y, it just takes any set and gives back the set. P composed y is p. So why do I use that weird symbol? Well, as I said, we want to reserve circle, but also this one almost looks like a circle. So when you write it fast, it looks like a circle. It's no problem. But also it represents trees with p under q. So it's as though the tree is growing upward from p, growing upward into q. So p is on the bottom and q is on the top. And it makes that stacking look good. So here, if I want to stack q trees on top of p trees, then I just find all the ways of doing that, and that's this. So this as a polynomial is y to the 6th, because there are 6 leaves, plus y cubed, plus y cubed, plus y to the 0, plus y cubed, plus y to the 0, sorry. So that's y to the 6th, plus 3y cubed, plus 2. And I can just read that off from that picture from here. Not that that's the easiest way to compute it, but just that that is a way to compute it. You can also read the symbol as q feeding into p, right? It looks like q is kind of being passed into p, which is, again, how composition works. So the directionality of this thing works for a lot of different reasons, and one more that we'll come to later. So what are comonoids in poly? I gave a whole talk where I explained Ammann-Oosthuizen's result using very combinatorial set theory pictures. Basically, here's what's going on. If you have any monoidal category, like poly Y triangle, but here MI tensor, I is a monoidal unit, then a comonoid is a triple consisting of a carrier, some object, some polynomial say, a map from that object to the monoidal unit, and a map from that object to its twofold tensor product. So these are the co-unit and co-multiplication, and Ammann-Oosthuizen proved that comonoids are exactly categories. So up to isomorphism, every category is a polynomial comonad, and every polynomial comonad is a category. And so what's the connection? Well, if C is a category, then here's the name of the polynomial I'll associate to it. It is the sum over all objects of the category. So the objects of the category become positions. And for every position, the set of directions is the set of morphisms in C that emanate from I. So it just collects all those morphisms sticking out of I, with I as a domain, and it takes that set and puts that as the exponent for the polynomial. Now, if you think, what functor does that really mean? There are ways of thinking about it, but I don't think that's really the right way to, I like to just think of this thing as a data structure. It's just a way of holding a lot of information about C. But it doesn't hold all of it, it just tells you the objects and the outgoing arrows of everything. So you still need the identities and other things. And the co-unit assigns the identities. It's a functor from this polynomial to y, which is like a delegation of decisions. Every position or object in C is assigned the one direction position, one direction decision. And that single decision thing is passed back to some option, some outgoing arrow from that object, and it turns out to be the identity. It's forced by the rules of comonoids to be the identity. And the co-multiplication assigns to every morphism its codomain and tells you how composites work. So this is what I talked about in this talk here. So in poly, comonoids are categories, but morphisms between comonoids are not functors. They're called cofunctors. And I write them with this little slash to indicate that you kind of like go up and back or something. It's kind of, yeah. Anyway, those are cofunctors. And what's a cofunctor? Well, it's a comonoid morphism. You just read off what that means. But what it really tells you is that for every object in C of 1, or in C, we get an object in D. And for every morphism coming out of that object in D, we pass it back to some morphism coming out of the object in C. It's kind of weird, feels weird at first. So what's a cofunctor from C to y to the n? This thing here is a category with one object, because there's only one position, and natural number many morphisms. And what I mean by this picture here, I mean the natural numbers as a monoid under addition. So what's a functor like this, a cofunctor? Well, it sends every object of C to the unique object here, but it sends every morphism back to a morphism coming out of that object. So it's basically a way of assigning to every object in C and every natural number a morphism coming out of that object. So it turns out that by the rules of cofunctors, the only one that matters is 1, what it does to the element 1, the natural number 1. So what eventually happens is that let me just tell you the answer, a cofunctor like this assigns to every object a single outgoing morphism. So it's like a vector field on your category. Imagine you have a category, any category you want, and just assign a random arrow sticking out of every object in your category. And that's a cofunctor to the naturals. And it's kind of, when I saw that, I was like, well, that's a weird thing to do with a category. Why would you do that? I mean, what's amazing is it turns out that those things form a monoid. That's closed under composite. You can multiply two such admissible, they're called admissible sections, by Marcelo Aguiar, who I think invented cofunctors, or maybe Higgins and Mackenzie, I've forgotten right now. But anyway, this way of doing things gives you, I mean, it's got nice properties, it does stuff, but it's kind of weird. So I think of it like a whole new world to explore. If you're used to thinking about categories, you may not at all think about cofunctors, where the principle of equivalence, for example, is not there. Equivalence of categories is not a cofunctorially interesting thing, but isomorphism of categories is. So it's kind of a whole new world to explore. And by the way, this kind of vector field like thing hints at applications, which we'll come to soon, maybe in 4 slides or so, I don't know. So Bico modules, I have been calling these bimodules, but people get confused. I just don't like saying so many syllables. But Bico modules in Poly are, if you have 2 comonoids, in other words, 2 categories, it's another kind of map. So cofunctors were very different than functors, but bimodules contain both. So a bimodule, you can just read this from the Wikipedia page or Bico module or the NLab page, is going to be another polynomial, I'll call it M, and a map of polynomials to C composed M and to M composed D. Just polynomial maps into composites. And they, of course, have to cohere with the comonoid structures on both sides. That, of course, by of course, I mean for any category theorist, you're used to that sort of thing. But I denote this bimodule or bicomodule like this because I see this M repeating 3 times and then these triangles pointing the same direction. So I just kind of needed a way to remember it all. And so that's how I write it. See a bimodule M from like this. And right, it helps me remember how the maps go. But maybe it looks to you like it's going the wrong way from D to C. And at first I was like, oh no, what do I do? Because I don't know, I like my notation to be a certain way or something. So I thought, is this bad? But it turns out it's okay, or even good from another point of view. And that is that Richard Garner explained in his hottest video that Bico modules, which we've denoted like this, can be identified with parametric right adjoints, parametric right adjoint functors, I'll call them Profunctors, that go from C set to D set. Okay. So it goes from D set to C set. I hope I read that right. So it goes from D to C in some sense. So if you read this as a bimodule, maybe you think of it going from left to right. If you read it as a profunctor, it goes, or a parametric right adjoint functor on Copriegev categories, it goes right to left. So it kind of depends how you want to read it. Do you want to read it as a kind of combinatorial object? Then I think it goes from C to D. Or do you want to think of it as a functor? Then it goes from D to C. And by the way, the polynomial functors, the one that we've been talking about this whole time, if C and D were just one, the one object category, then this thing would just be poly again. So you can either think of polynomial functors as combinatorial objects, then you think of them as bimodules, or you can think of them as functors, then you're thinking of them as this sort of thing. Anyway, I hope, yeah. So from this perspective, the arrow points in the expected direction. And I just wanted to go through with you a little check. What happens if D is 0? I want to show you that that's C set, the category of functors from C to set. So let's say D was 0, the 0 object category. Then D set is the set of functors from D to set. So it's the functors from the empty category to set. And there's exactly one of those. So it's parametric right adjoints from 1 to C set, and every functor from 1 to C set is a parametric right adjoint. If you don't know what a parametric right adjoint is, it's a functor that preserves connected limits, at least for functors of this form. So basically, we just calculated that since every functor from 1 to C set preserves connected limits, that we have this isomorphism here, or equivalence. I think it's an isomorphism. Oh no, it's an equivalence. It's an equivalence. It's more like discrete op vibrations over C. Okay, so these bimodules generalize profunctors in the following sense. A profunctor from C to D is a functor, in my way of thinking, is a functor from C op times D to set, or you could think of that as a functor from C op to D set, or as a functor from C to D set op. And this is the one that I think of as the one that's being generalized here. It's a functor from C to D set up. This bimodule from C to D is a functor from C to the free coproduct completion of D set up. So let's say both C and D were the one object category, then this would be functors from the one object category to, well, okay, we can just forget about that part because functors from the one object category to anything is just this thing. So if D was the one object category, then D set is just set, and we get the free coproduct completion of set up, which is what I said poly was in the beginning. In other words, one bimodules is poly. So I'll tell you how to think about this concretely when we get to applications. But this is how these pictures, these bimodules, generalize profunctors. So there's a frame bicategory that I call P. It's got polynomial comonoids, cofunctors, and Bico modules, and they form this nice structure. It's got two monoidal structures. It's got other nice limits and stuff. And despite the last slide, it's not actually that hard to think about. So here are some facts. I'll build up the CD bimodules in 3 steps. First of all, the D0 bimodules, we said it was D set. It's the category of co-precisions on D. Then 1D bimodules is you kind of flip this thing around, you op it, and you freely co-complete it under coproduct. And what is the free coproduct completion? It's not so bad. It just means you have sets of D sets. Each one, an object in here is just a set of D sets, and a morphism goes from one set of D sets to another set of D sets and backwards on the co-precisions. Okay, anyway, so this one is D set. This one is the free coproduct co-completion of it. And this one is just functors from C to the previous one. So if you want to look at CD bimodules, you can just think of them as the functors from C to the 1D bimodules. And the 1D bimodules are not so bad. So you can think of, in some sense, this guy is the main character because you're used to thinking of functors from C to things as relatively the same, as, we understand arbitrary C, so what is this crazy thing here? Well, you can think of it as something like the polynomial rig in D. If D is discrete, then you get the rig of polynomials in these formal variables, one for every element of J. Okay, so if D is a discrete category like 2, then this would be the rig of polynomials in 2 variables. And so in Gambino and Cox paper, they give a frame by category, but they're only looking at where I and J are discrete categories. And so what is this? They tell us it's I many polynomials in J variables. Okay, but for a general D, I guess what is this D set op and why do I like it? I like it because it's the free limit completion of D. So y to the blank is a functor from the Uneta embedding from D to the free limit completion of D. And so what we're doing when we look at 1D bimodules is we're just generalizing from sums of products in a set, like sums of products are polynomials, to sums of D limits. So it's like if you had this category D with like objects A, B, and C, and a map from A to C and a map from B to C, then you could just kind of write those formal diagrams as though they were, you know, instead of y cubed, you could have y, you could have this limit cone instead of y cubed. Okay. So operads are examples of more monads in P. In any frame by category, a monad consists of an object in the frame by category, you might call it the type, a bimodule from that object to itself, you might call that the carrier of the monad, and then a two-cell called the unit and another two-cell called the multiplication. And I know this is getting pretty technical here for some people, and soon we'll get to the applications. I think one more slide of theory here. And so these generalize operads in another number of ways. If the category is discrete and the two maps here are called Cartesian, in other words, these kind of pullback maps are isos, then you get colored operads, I many colors. And so this is not quite the standard definition of operad. It's one I like better. It's that the input to a morphism is a set rather than a list of objects. So that kind of bakes in the symmetry or free symmetry. You can also talk about standard operads and generalizations, various generalizations within this P setting. You would just kind of slice over various things that told you what do you want lists or what kind of operads do you want? And so just see the Gambino-Cock paper for how to do that. If you relax the discreteness of C, which we'll see on the next slide, then it allows the input of a morphism to be a diagram rather than a set of objects. So imagine an operad where with that little triangle with 5 lines coming out of it and 1 line coming out the other side. So 5, the domain has an arity of 5. Instead of that 5 being a discrete thing, imagine it was a limit diagram from C. That would be kind of how you think of the more general, this single relaxation from going to from a discrete thing to an arbitrary category. The inputs to your morphisms can be diagrams rather than sets of objects. And if you relax the iso condition, so you don't make these things Cartesian, then the composites and identities can have kind of weird arities. The identity might not have one input and stuff like that. But it still takes care, like the monad laws still do their work. The identity still acts like an identity, but in a kind of strange way. Or the composite might have too many or not enough incoming arrows or incoming domain objects, it might seem like, but it still works monadically. So for example, every Grothendieck site gives you a P-monad. Let's say you have a category C-op, so that I get to say that co-presheaves on C are might be sheaves or not. So I'm putting everything in my direction or in a way that works for this thing. So you have a Grothendieck site on C-op, and I'm going to be considering C. This thing has an associated monad in P. So a J sheaf will be an MJ algebra, but not vice versa. An MJ algebra might not be a J sheaf. So it's not we're not recovering the topos of J sheaves. We're just getting the algebraic data of a sheaf. So an MJ algebra, when you want to glue things together, you've got a compatible family. It will give you the existence of a section gluing them. Not only existence, it'll give you a formula for the section generating them, but not necessarily any sort of uniqueness. And the idea is if you had a Grothendieck topology J, I'll give you on your category C, I'll give you a monad on C. And what is it? I'll just remind you what a Grothendieck topology is. It assigns to every open set or element object of C, it assigns a set of covering families. Which sets of open sets cover your set, your open set? And to every family, you assign this sieve, this subfunctor of the maps coming out of V. If you're thinking pre-sheaves, it's the maps coming into V, but I opt it. So from this data, we define our monad. Our monad, our polynomial says, for every object V in your category, And for every covering sieve, I want you to tell me information about all of the well, I'll put this subfunctor up here, the set of elements of the subfunctor there. And the Grothendieck topology axioms, there are 3 of them. One of them gives this M a bimodule structure, and the other 2 give it a monad structure. And finally, if I had an algebra on M, so if I have this, parametric right adjoint from C set to C set, and I plug in my C set P, my co-presheaf P, then I give this map H to P, and this data will say, for every covering family of some V, what section of V do you want me to call its glue, or its glued together thing? It doesn't tell you that it's unique, but it just gives you a formula for gluing. So if you had a unique one, like a Grothendieck a sheaf, then you would have an algebra structure, but not vice versa. Okay, so that's kind of the theory part. Now let's talk about applications. So applications. So a Moore machine, which I'll draw like this, has an input set and an output set and a set of states, a set whose elements we call states. And every state gets a readout, gets a B called readout, so a function from S to B, and a function called update that takes an S and an input A and gives you a new S. And we would further say it's initialized if you have an initial state. And so this here, A, is called the input set, and this is called the output set of the dynamical system, of the Moore machine. So for dynamics, what it does is it takes a stream of A's and gives you a stream of B's. If I had a stream of A's, then I already have this S0 as an element, and I'll just let Sn plus 1 be the update of the nth state with the nth input. And I'll let Bn be the readout of the nth state. And so I'll get a list of Bn's, Bi's for all I. So that has turned my stream of A's into a stream of B's. And this all really works because, turns out that this really works because this thing is a comonoid. And that's why I reached out to Joachim and saw the Garner video. So what I'll explain that. So how do we see this in terms of polynomials? This map S to B and S times A to S is exactly what a polynomial map SY to the S to BY to the A encodes. So phi, like the phi1 thing, the map on sets goes from S to B, that's the readout, and phi sharp going from S times A to S is the update. And we would give an initialization by giving a map from Y to SY to the S. And so you can generalize this instead of forcing this guy BY to the A to be, that special form, this monomial. You can allow the P dynamical system or P Moore machine to have arbitrary or different input sets for its different outputs or its different positions. So imagine, instead of, when you think of output, you think you're like sending a signal, but imagine that that signal is like, is kind of like your position, your point in position. It's like your position in signal space. And so for every position you're in, but now instead of, now you can kind of like move around a field or something like that. You can be in a tunnel sometimes or be out in the open other times. And given where you are, you might have different inputs. So it's the same sort of thing. Every state gets a position, and for every direction at that position, you get a next state. Okay. In fact, more generally, you can go from SY to the S, a cofunctor to an arbitrary category C. For example, what we talked about before, this SY to the S to BY to the A or to P, can be identified with a cofunctor from SY to the S to the co-free comonoid on P. And that's just a formal thing. You don't have to worry about it. But all I'm saying is that I'm generalizing even more from this Moore machine to arbitrary polynomials here, and then from a map from this comonoid to a polynomial to a map from this comonoid to a co-free comonoid or to any comonoid. In other words, any category. Okay. So you can have a wiring diagram where a bunch of dynamical systems are interacting within another dynamical system like this. Inside of each of these PIs, we're going to put a dynamical system like an SY to the S mapping to P1 and a ty to the t mapping to P2 and all these things. And we'll tensor them all together and get a dynamical system in the Q. So what's going on here is that each box represents a monomial in this very particular picture here. This box P3 would represent the monomial C times y to the AB. So C is in the kind of positive position, the output, and A and B are in the negative position, the input. And this whole interaction where P1 sends its outputs to P2 as inputs, et cetera, and to P3, all that is captured by a map of polynomials from P1 tensor P2 tensor P3 tensor P4 P5 to Q, where Q is this outer box there. And I didn't tell you what tensor means. Tensor of polynomials, you just multiply the positions, and then in every position, I prime, position in P and a position in P prime, the directions there are the product of the directions in P and the directions in P prime. It's a very simple operation. And this wiring diagram is a map of polynomials. And so given the positions, if you knew what each one of these guys was outputting, then this morphism phi would tell you what this guy's outputting. And if you knew what was coming in on the inputs, then you would also get an input for all these guys. So that's, yeah. So a map of polynomials gives you a wiring diagram, or at least every wiring diagram gives you a map of polynomials. But a map of polynomials is more general. It allows the wiring diagrams to change. So imagine a company could choose which supplier it wanted to input from. So part of the company, what the company kind of outputs is who it wants to get as its supplier. And so it can change its wiring diagram. And this whole picture here is supposed to represent one morphism in poly, not two different morphisms. So this whole picture here is one morphism in poly. And I think I'm not going to go through it in detail, but it's on the slide and I'm happy to talk about it more. I think I've talked about it in detail in other talks. So yeah, so in these dynamical systems, the company dynamical system is choosing its state is being updated based on what it's receiving. So it's receiving stuff from this supplier for a while, updating its state. And then one day it gets into a state where it says, you know what, I want to change my position. I want to now receive from supplier 2. And the way I've set up this function, this morphism of polynomials, when this company is in its second position, it can unilaterally dictate that it receives from supplier 2. Based on this thing, you can make it so that they vote on who supplies it, or that company 1, the company always decides and stuff like that. And that's kind of how I hope, that's kind of how you like pick up an object too. Somehow you unilaterally decide to be able to pick up that object, and it doesn't seem to have a vote. And so all of the atoms in our universe somehow collaboratively vote on who's going to connect to who. Maybe that's how we can think about it. Okay, so there are other sorts of dynamical systems. I usually call these dynamical systems because they're systems that change through time, but that's not usually the definition. So the usual definition is that you have an action of a monoid. Maybe a discrete dynamical system is you have an action of the natural number monoid, or reversible is the integers, or real time is the reals. And if T is a monoid and S is a set, then a T action, which is called a dynamical system, is equivalently a map from S times T to S, satisfying 2 laws, which is equivalently a cofunctor from Sy to the S to Y to the T. Y to the T is my monoid T, and this cofunctor, to be a cofunctor means to satisfy the same 2 laws as the action. So what that means, what I'm saying, okay. What I'm saying is that we're generalizing what we said above. Sorry, our general picture of Sy to the S mapping to a category C also does include the typical definition of dynamical system. This is not including continuity or measurability or things like that. You'd need a different category of polynomials to do that sort of thing, although I haven't really looked into it. But it does capture at least a set theoretic version of an arbitrary kind of time for a dynamical system. The next application is databases. So one view on databases is that they're basically co-presheaves. So here I have a little category with 2 objects, 1 employee, 1 department, and some foreign keys, they're called, that every employee works in a department, every department has an admin person, every employee has a manager, and that the department admin works in that department. So if you look at the department, you look at their admin person, you ask who they work in, it's the identity on department. So C is a little category given by generators and relations, and a functor from C to set, in other words, a C0 bimodule, can be represented with a bunch of employees, a set assigned to the dot employee 1, 2, and 3. The set assigned to department is 101, 102. These are not natural numbers, these are just identifiers, and just elements of a set. And works in, this arrow here gets sent to a function, the function that sends employee 1 to 101, and 2 to 101, and 3 to 102. And manager is a function from employee to herself. But the first complaint is that where's the data? Like, where are the employee names? Why is it all meaningless identifiers? And so to get that into the picture, to get attributes into the picture, like Alan, Ruth, Sarah, for every employee has a first name, and every department has a string associated to it also. Sorry, it's kind of jumping around there. We assign a co-presheaf to the objects of the category. So we just take every object and give it a set, like the type for employees is strings. And then using the canonical cofunctor from C to obc, you might say, well, that's not the way a functor goes. It goes from obc to C. Well, cofunctors go from C to obc because every object of C gets sent to an object, and then every morphism here is passed back. And so the only morphisms here are identities, and they have to be passed back to the identities. So there's a canonical cofunctor like this, and here's our data, our meaningless data, and here's our types, and alpha is the attributes, assigning every employee to like some string. Okay, so now we're seeing bimodules, cofunctors, 2 cells. We're getting full use, almost full use of our frame by category P. The last part of the frame by category is composition in the horizontal direction, and that is also useful in databases. Those are the data migration functors. They're parametric right adjoint functors. So a parametric right adjoint is understood, as we said, as a functor from C to the 1D bimodules. And every object in C is thus given a 1D bimodule, in other words, a formal coproduct of formal limits in D. So what's a formal limit in D? A formal limit in D would be called a conjunctive query. And you can always force these things to be finite if that matters. You can say, I only want to consider the finite polynomials or whatever here. So anyway, we get these conjunctive queries on D. Those are the formal limits. And so a profunctor from 1 to D is a disjoint union of conjunctive queries. Maybe I'll call it a duck query. Okay, so disjoint union of conjunctive queries. What is that kind of like? Well, if D is this little category, cities are in states and counties are in states, then a duck query is a disjoint union of conjunctive queries. It might be something like, okay, give me every pair of cities in the same state, plus every pair of counties in the same state, plus every city and county that are in the same state. And that's what I want you to tell me the set of. And so those disjoint unions of conjunctive queries, those duck queries, are exactly the bimodules from 1 to D. And so a general bimodule from C to D is just a functor from C to duck queries. Every object in C is given a duck query on D, and every map in C is given a way to take the answers to duck query 1 and give you answers to duck query 2, a function, or that's what it turns out to be. So it's just a way of assigning any answer to the first query to an answer to the second query. The last application is cellular automata. So here's a picture of a glider from Conway's Game of Life. What's going on here is this little picture here transforms into this little picture here, which kind of transforms into this picture again, maybe rotated one. And they just keep going down and down and down the page as you make a certain kind of transition. So let me break it down a little bit. So the Game of Life takes place on a grid, say a set V of squares, say the integers times the integers or whatever you want. And every square has some neighbors, so we think of the grid as a graph. Maybe every vertex has 9 neighbors, including itself, or 8 neighbors, depending on how you count. We'll say 9 today. So each square, finally, each square can be in one of 2 states, either white or black. And then, I guess it wasn't final after all, there's one more thing, which is that any state is updated according to a rule. If the square is black, and has 2 or 3 black neighbors, it stays black. If the square is currently white and has 3 black neighbors, it turns black. Otherwise, it turns or remains white. So we can see why this thing is black, because it was white, but it has 3 black neighbors. This one is black and has 3 black neighbors. This one has too many black neighbors, 5, I guess. Right, so that's the update rule, and that causes this little thing to kind of run down the page. So how do we encode this in P? Sorry, again, this slide is going to kind of jump around. My LaTeX is not great, I guess, for these things. So we encode the graph. Here's the graph, arrows and vertices, or neighbors and vertices, as a profunctor, wow, from V to V. Okay, what it says is, I'm going to migrate data from V to V by querying my 9 neighbors. So the carrier of this profunctor is Vy to the 9th. And one thing I really like about Poly is that often the polynomial, when you look at it, it reads like what it's trying to say. So it's kind of telling you about that 9-ness in it. And so yeah. So the profunctor is Vy to the 9th. That's what goes here. And there's a map from that thing to, you know, Vy compose Vy to the 9th, etc. That's what this bimodule is. And anyway, so we encode the color set for each node as a profunctor from Vy to 0. So every V gets 2 colors. And so this C, this polynomial here, is the constant 2 times V. So yeah, every vertex gets 2 colors. And now I just write this out as a map. The update is a map of profunctors. It says, okay, suppose I have a vertex and I query its 9 neighbors, and for each one of them I have a color, black or white. Then for every element of that set, I want you to give me a new color. So for every 9 neighbors' colors, what is my color next? So that update formula that I gave like here is encoded in that update, in that U there. And finally, the initial color setup, you like color your whole grid, your Conway game of life thing with some random color. What that is, that initial thing is a map like this from the terminal V0 bimodule to the color set. And now you can run this machine. You can kind of just run it over and over and over, and to see how the cellular automaton evolves through time and the glider moving down the page. Okay, so I tried to pack a lot in, and it was pretty packed. But again, this was supposed to be a calling card. Like, if any of this interests you, please call me. I think in terms of future work, well, I think at least American society, but probably worldwide, right? There's just lots of unhealthy behaviors as a species, as individuals, but we don't know what unhealthy behavior is. I mean, if we could communicate it clearly, maybe we could get something going, but we don't exactly know what healthy and unhealthy mean, and we don't know what activities are necessary for survival, right? We don't know how a new choice we make is, whether it's going to help us or not. And we don't really seem to know how to communicate so that what needs to happen does. It's not getting through. And I don't know if Poly can help. I mean, you might say, well, good luck. But I mean, it's got so many neat things that seems close that I'm hopeful. I think maybe if we can think about these questions mathematically, have real grounded discussion, something we can point to like math, and if we can make philosophical and mathematical progress, we can try to echo it in tech. And then if we can make technological progress and it's actually good, people will take it up. That's one thing you can count on people for. If they think something is convenient and useful, they will use it. And so if we make healthier tech systems that take into account what healthiness is, or like what makes communication work, then it might actually help with this various crises that are going on now. And I don't know how promising that is, but it's as promising as any direction that I know of. So that's kind of where I'm going. It's both interesting and maybe possibly helpful. I wanted to advertise a functor. I wanted to advertise a workshop coming up in March. So Joachim and I are organizing this Poly workshop coming up in March 15th through 19th. And we've got all sorts of great speakers here lined up. So if you're interested, the website is here, but I also sent an announcement to the categories list and types list, and just reach out to me if you're interested in attending. And what's happening this moment right now, this colloquium, is the first in a series of colloquia. There's more information here. We've got some great speakers lined up. Richard Garner is speaking next week, and then Gunnar Carlson, and then Samson Abramsky, and a bunch of others. So please join us. Yeah. So in summary, Poly is a remarkably abundant category. It's completely combinatorial. It's set and set up, basically. It's free coproduct completion of set up. But what is it? The calculations are totally concrete, and it's already pretty familiar, like this thing. I mean, this was drilled into me so much in middle school, like it's just kind of like a friend for some reason. But it's also theoretically beautiful. Comonoids are categories, coalgebras are co-presheaps, monoids generalize operads, and it's got this wide scope of applications from databases and data migration to dynamical systems and cellular automata. So like category theory itself, it's this very tight little setting, a single setting for pursuing real philosophical and technological progress. So thanks for your time and attention.
That's great. Thank you, David. I will, I don't know what the etiquette is, so I will virtually clap for you on Zoom.
Thank you.
So we've got some time for some questions now. So the way, I'm not sure what the best way to do this is, I've got 1 or 2 questions in the YouTube chat that I might pass over to you, David. If anyone else has a question, stick it in the Zoom chat or the YouTube chat, and if you're on Zoom, I can maybe unmute you if it's a long enough question. So feel free to post. We have one here, David, from Morgan Rogers on the YouTube stream, who says, going from Conway's game of life to formalizing something like healthy behaviors is quite a big leap.
Yeah.
Do you have any ideas on how to break it down into kind of interim steps that are maybe a bit more concrete?
Yeah, thanks. That's a great question. So there's someone named Daniel Polanyi working on something called empowerment. Empowerment is a purely information theoretic idea about that what every agent is trying to do, instead of we give them arbitrary rewards in reinforcement learning, instead what every agent is trying to do is trying to maximize its the channel capacity or mutual information between what its actuators can do now, like what its its positions can be, I guess, and what its directions will be in the future, what it's going to sense in the future. So when that channel capacity is 0, that when the agent is dead, the channel capacity is 0. So if you try to maximize that thing, you automatically try not to die, but you're also trying to basically give yourself as much understanding of what the future will look like based on what you do as possible. So I think that's pretty neat. Can that be made compositional? I don't know. Or